Today I'm talking about audio and other kinds of waveforms. My goal is to give you techniques you can use to store and then later reproduce waveforms, primarily audio, but others as well. The kind of waveforms we're talking about are time-varying scalar values. In the control theory literature, this is commonly referred to as a signal, and I may use that term as well. The example that we're most interested in is sound, which is actually air pressure over time. And here's an illustration of what that might look like. Time goes from left to right, and we have the air pressure going up and down. This is what you're hearing, and when you're listening to me, you're actually hearing such a thing. Raster video is actually brightness over time, more or less the same thing. And you can imagine other signals, which would include things like speed over time, position over time, and so forth. A very fundamental property of signals, especially periodic signals, is that you can decompose them into a sum of harmonics. That is to say, a bunch of sine and cosine functions whose frequencies are a multiple of the base frequency. So in particular, if you have some smooth function f of t that has a period capital T, that is to say f of t is f of t plus capital T, this means that unless your signal is really crazy, and sound does not count as a really crazy signal, there are some coefficients, the a's and the b's as I've written here, where you can rebuild the waveform by summing up a bunch of sine and cosine functions. To illustrate how this works, consider trying to reproduce a square wave by adding up a bunch of sine curves. Here is the fundamental, and it sounds like a very pure tone. This is a 440 hertz sine wave. To get the next component, we add something that's 3 times that frequency, but 1/3 the amplitude. And here's what that sounds like. Next, we add something that's 1/5 that amplitude, 5 times frequency. Here's 7 times the frequency with 1/7 the amplitude added in. Here's 9 times and 1/9. Finally, here is what your speakers or headphones thinks a square wave sounds like. I guarantee you it's wrong, but it's closer to what we've heard before. The basic observation is that nothing changes infinitely fast, including sound pressure waves. Realistically, you can always bound the rate of change, and this is essentially limiting the bandwidth of a signal. Typically, you talk about the bandwidth as being a maximum frequency in hertz, meaning per second. Here's an example of this. So this is the waveform that was traced off of an extremely expensive audiophile amplifier rated all the way from 5 hertz all the way up to 120 kilohertz, way beyond the range of human hearing. And you can see, even with such an expensive amplifier, it takes some time for the value to change. The edges are a little bit rounded off. This always happens, and it actually sounds fine. While Fourier did not figure out how to do his transformation until the early 19th century, nature beat us to it. It turns out, if you look very carefully inside our ears, you will find essentially what is a physical Fourier transformer in the cochlea of the ear, which is essentially a long cone that's wrapped around into a spiral. The diameter of the cone at every point affects the frequency response. The result is we hear high frequencies near the base of the cochlea, where the ear begins, and low frequencies near the apex of the cochlea, that is, the tip of the cone. When you're trying to reproduce sound, it's good to know a little bit more about human hearing. A good number to remember, keep in your mind, is that humans can hear roughly 20 hertz, that is 20 times a second oscillations, all the way up to 20 kilohertz. Now, this is a very rough thing and varies per individual. In particular, highest frequency you can hear tends to reduce with your age. So for example, when I was a kid, I was driven crazy by the sound of TVs because of their 15 kilohertz horizontal refresh. I can't hear that anymore because I'm too old. Another way to think about this is an 88-note piano covers a pretty big range of it. It does not have the super highest tones, but these tend to be overtones that you can hear. And the things that often show up are things like hi-hats and other percussion things often have a lot of energy at the higher frequencies. If I make a sound like this, shh, you actually have quite a wide variety of frequencies represented. Another fundamental concept to know about when you're dealing with audio is the Nyquist Theorem. And it states that if you want to reconstruct a bandwidth-limited signal, and you're doing it by sampling, that is to say, gathering a value periodically, you need to sample at least twice the maximum frequency you want to receive. Illustrated here is sampling at 8 times the frequency that you want, and as you can see, it's not that hard to reproduce the original signal. Similarly, if you sample at 4 times the frequency, you can still see it's getting a little ragged, but you could still imagine reproducing the original waveform without too much difficulty. At twice the frequency, it gets pretty tricky, but you could still do it if you smoothed out the result enough. The problem is, if you go above this, you start getting the possibility of aliasing, and this is exactly what happens. You sample a high frequency and you end up actually perceiving different frequencies. Here we are sampling at just slightly above the frequency, so this is 4/3, and if you look at the straight lines here, they're actually look like a much lower frequency, not what we actually have. And even more, here we are sampling at exactly the frequency itself, and we've managed to sample in such a way that we are hearing silence. This we do not want. Here's another nice diagram that illustrates how our ears respond to different frequencies, and in particular, how they respond at different frequencies with different levels of sensitivity. In particular, really low frequencies have to be fairly loud before we hear them, whereas reasonably high frequencies, say in the 2 to 5 kilohertz range, we're actually quite sensitive to it. Another interesting thing is to see speech. The sound there sort of peters out around, say, 8 kilohertz, something like that. So a common trick is, if all you want to do is communicate speech, limiting the bandwidth to, say, 8 kilohertz, something like that, is really quite effective. And this is what telephone networks did for many years. They realized mostly what people want to do is talk on the phone, not listen to music. So to reduce network bandwidth requirements, they reduced the sampling rates to 8 kilohertz. Nyquist tells us that if we want to reproduce frequencies up to 4 kilohertz, we need to sample at 8. I've just imposed a 4 kilohertz low-pass filter on my voice. Not a dramatic change, really. This is roughly what the best telephones used to sound like. Here I've run a 1 kilohertz low-pass filter over my voice, and you can see now it's quite muffled. You can still hear what I'm saying, but it sounds not very natural. Even more extreme, here is a 500 hertz filter. We've been talking about frequency issues. Now let's talk about amplitude issues. Any signal in the real world, be it sound, image, anything, there's always something that makes them deviate from some ideal. The Fourier transformation is pure mathematics and a very powerful one, but assumes that you have perfect knowledge of the signal in question. In practice, you never do. There is always some source of noise that makes the signal deviate from the ideal. Engineers speak in terms of signal-to-noise ratio, which is a ratio of powers, the signal power versus the noise power. Because of the nature of signals, this signal-to-noise ratio is usually measured in decibels. In particular, it's the ratio, log base 10, of the power of the signal to the power of the noise. While dB is a useful number to think about noise, it's not very practical if you're doing computer stuff. Because dB is logarithmic and bits are logarithmic, you can very exactly calculate how many bits gives you kind of signal-to-noise ratio. Each bit gives you roughly 6 dB worth of less noise. For example, CD samples, which are considered reasonably high fidelity, end up being about 98 dB worth of signal-to-noise ratio, and this is about the range of human hearing. On the scale on the left, we can see all the way down, 0 dB is defined as the lowest at which humans could ever hear, which is very, very, very quiet. You need something like an anechoic chamber to be able to get something that quiet. Whispering might be in the 20 to 30 range. Residential ambient noise is 40. In the New York area, it's probably more like 50 or 60. 60 is the average conversation. 70 is your loudmouth friend. 80 is where you listen to music. 100, 110 is the subway. 120, 130 is when it becomes painful. 140 is shooting a bullet. 98 dB is plenty for sound. Most of the time, if you actually have a 98 dB source, your amplifier, your speakers, are going to introduce more noise than that source. So that's more than enough. If you want to represent sound waveforms in memory, here is the expression of how much it costs. So you look at the number of samples per second. This is the sampling rate, and remember with Nyquist, you can only get half the frequency of the samples per second. So if you want a maximum frequency response of 8 kilohertz, you need to sample at 16 kilohertz. You have the number of bits per sample. 16 gives you CD quality audio. 8, 10, 12 gives you something more like a telephone, which is acceptable. Then if you want to do, say, stereo sound, you might have multiple channels. From there, you can calculate, depending on how many seconds of samples you want to save, how many bits you need to store. So let's take an example. A CD is stored at 44.1 kilohertz, 16 bits per sample, 2 channels. And so you multiply it through all of that, that's 1.4 megabits per second. That's 175 kilobytes per second. So for a 74-minute CD, that's the maximum length, you multiply all that out, you end up with 783 megabytes. And that's roughly the capacity of a CD. It's different when you store data on a CD because they put more error correction on it. But that gives you the rough idea of how much memory you need to store, say, 74 minutes of high-quality audio. The number of bits per sample, the number of channels, the sampling rate, all can contribute to saving memory if you are representing samples. We just saw that 74 minutes of CD quality audio ends up being 783 megabytes worth of data. However, if we switch to 74 minutes of telephone quality audio, that is to say we're using 8 bits per sample, which is reasonable. You can hear the difference, but you can still hear what's going on. A single channel, and then only sampling at 8 kilohertz, 74 minutes then gets reduced to only 35 megabytes, which is substantially less than 783. Reducing the number of bits per sample, the number of samples per second, the amount of time you're recording, the number of channels, all of these can reduce the amount of data you need, but maybe you can make better use of the bits you have. This is called compression. With audio, you can usually do lossy compression. That is to say, not reproduce the waveform perfectly, but reproduce enough of it so that it sounds good enough for people. One of the most basic ways to do this is a mechanism known as companding. What this does is it still stores 8 bits per sample. However, rather than using linear pulse code modulation, it uses nonlinear, slightly exponential. And what this does is each 8-bit sample is actually projected up to 12 bits worth of dynamic range. The difference between quiet and loud is larger. However, you trade that for more quantization noise. Now, it turns out this is a reasonable trade-off, and this was another trick that was employed by the telephone systems for many years. And so if you look up mu-law or A-law compression, you can see the algorithms for doing this. And this is what this diagram is all about. The next step up in audio compression is known as ADPCM, Adaptive Predictive Pulse Code Modulation. What the decoder does is look at the last few samples, make a prediction of what the next sample might be based on that. It's a pretty simple predictor. Then uses the data in the data stream to decide how wrong it was and then correct its result based on that. So broadly, it's using the difference between the next sample and the predicted value, encoding that. And this gives you roughly a factor of 2 in compression. Not bad. Perceptual coding is now the state-of-the-art in audio compression. This is MPEG Layer 3 or MP3, which you may have heard of. This took the world by storm in the mid-90s because it could get enormous compression ratios, like 100 to 1 or 1,000 to 1, and still sound pretty reasonable. It relies on understanding the human auditory system, and in particular understanding how loud noises mask quiet noises that are similar in frequency. Sound comes in, it is transformed into the frequency domain through a Fourier transformation. Using a psychoacoustic model, it goes through and removes things that it thinks won't matter in such a way that there's less information. Then it figures out how to quantize that, code that, compress that, all kinds of other tricks. It's very elaborate algorithm. The fact that we can do this at all is pretty remarkable, and today you can easily pick up MP3 chips without too much difficulty. It is a complicated algorithm, not something that you want to try to implement directly. You want to steal somebody else's implementation. What I've spoken about so far assumes that someone has given you a waveform and your goal is to reproduce it somehow. A very different approach to generating sound, say, for a video game, is to think in terms of, well, what waveform do we want in the first place? What I'm talking about now are synthesis techniques. So the idea here is that we are generating a waveform, not that was given to us, recorded by a microphone, but rather that something that is generated by an algorithm of some form. Electronic music has existed for a reasonable while. Important milestone is the Moog synthesizer, and I'm showing you one here. The way this works is it has piles of oscillators, noise sources, envelope generators, and filters, all driven by a keyboard with patch cords and dials all over the place. What's amazing is that you can get music out of such a contraption. Here is one of the very early amazing Moog synthesizer produced albums. This is Wendy Carlos's Switched on Bach. Here's another piece done by Giorgio Moroder quite a bit later. It's called The Chase. Moog is an example of so-called subtractive synthesis. The principle here, which is based on the human vocal tract, starts with a somewhat raw sound source. So that might be a square wave, a sawtooth, noise, something like that. Then it's passed through a series of shapers. So these are high-pass filters, low-pass filters, envelope control, things like that. This is what our vocal tract is doing. We have a larynx. It makes a buzzing sound. We then control the sound that we get out by moving our lips, our tongue, the inside of our mouth. Overall, it's an effective system for generating a wide variety of sounds, starting from a few bass sounds. In 1978, General Instrument developed a subtractive synthesis chip designed to be controlled from a processor. This is the AY3-8912 programmable sound generator. It had 3 tone generators plus a noise generator feeding into mixers with envelope control and then eventually going out to D to A converters to generate sound. It was designed to be operated under processor control. So all of these functions, the oscillator frequencies, the envelope, all of these were under register control. Many arcade games in the 1980s used these chips. Perhaps one of the most extreme was a game called Gyrus by Konami that contained 5 of these chips. Another sound synthesis technique that became very popular in the 1980s is known as FM synthesis. FM, or frequency modulation, is usually associated with FM radio. The principle is this: you have a carrier frequency, this is the frequency you are tuning your radio to, and to modulate it, you actually bend the carrier frequency a little bit. You increase it a little bit, you decrease it a little bit, and the deviation in frequency from the base carrier and what actually gets transmitted is the amplitude of your signal, your modulation. Normally, with FM radio, the modulation frequency is much less than the carrier frequency. In FM audio synthesis, you run the modulator and the carrier at nearly the same frequency, and it turns out that you get very interesting musical results. It's quite easy to implement this in digital hardware. All you need is an oscillator whose frequency can be controlled instantaneously by something else. In the case of a digital device, all you need is something like a sine table lookup that you can step through at a different rate. So these things are easy to implement and ended up being the sound of 1980s pop music, thanks in no small part to a synthesizer known as the Yamaha DX7. Virtually every piece of pop music featuring synthesizers in the 1980s used some FM synthesis. Here's the intro for the Motels' Only the Lonely, recorded in 1981. Here's Madonna's Like a Virgin from 1984. Here is a-ha's Take on Me from 1985. Here's a summary of how to generate audio waveforms. The most basic is direct sampling. This uses pulse code modulation. It represents the amplitude of the signal in binary, and the choices you tend to have are what the sampling frequency is. Nyquist tells us that if you want to reproduce, say, 10 kilohertz, you need to sample at 20 at least. You can also control the number of bits per sample. This is a trade-off between memory usage and signal-to-noise ratio. 8 bits is sort of reasonable but not great. 16 bits is CD quality audio and better than most audio systems. To step from there, consider lossy compression. The simplest version of this I know of is companding. This is running a non-linear filter through your audio and converting, say, 12-bit amplitude numbers down to 8-bit. You get more dynamic range, but the signal-to-noise decreases. ADPCM is a predictive mechanism. It looks at the last few samples, makes a guess about what's coming, then adjusts that guess based on the data that's stored in the file. You get a factor or 2 off of this. The most effective compression for audio is so-called perceptual coding, and this takes advantage of structures, behaviors of the human auditory system. In particular, it looks for loud noises with quiet noises near it, because it knows that we can't hear the quiet noises and gets rid of them. MP3 uses this technique. A very different approach is to consider sound synthesis. Rather than starting with a waveform and saying, I want that, you instead think, oh, I have a bunch of hardware. What kinds of sounds can I generate with it? So subtractive synthesis works by starting with some basic oscillators, say a square wave or a triangle wave, runs it through some filters to change the tone a little bit, then runs it through an envelope to make it sound a little bit more musical. This is the Moog synthesizer, for example, or the GI chip. FM synthesis was very popular in the 1980s because it's very easy to implement. All you need is an oscillator whose frequency can be controlled instantaneously. And it turns out if you control the frequency of an oscillator right around the speed at which it is oscillating, you get very interesting musical effects in the spectrum of the generated signal. Just about all synthesized music in the 1980s relied heavily on FM synthesis. I want to talk briefly about images. They are two-dimensional waveforms, and as a result, have many of the same considerations. The big difference between images and audio is the quantity of data involved. A relatively low resolution image, 640 by 480 pixels, this is about as good as what television was before the HD world. If we represent things with 24 bits per pixel, this is 8 bits per red, green, and blue, you get a pretty good image, but a single frame requires 900 kilobytes to represent. This is a lot of data. If you start looking at HD, 2K displays are 1920 by 1080, and again 24 bits per pixel. It's nearly 6 megabytes just to represent one frame. And as soon as you start talking about video, amount of data involved is just insane. As with audio, some of the best image compression algorithms rely on behaviors of the human perceptual system. A relatively successful one is JPEG, and this is for still image compression. and they pull out a lot of tricks. So one of the things they do is, even though it starts with an RGB image, it is quickly changed into a different color space where certain aspects can be more easily thrown away than others. In particular, the human visual system is more sensitive to changes in brightness than in tint. It also uses Fourier transformations, or the equivalent thereof. It quantizes things, uses almost an ADPCM style compression at one point. In the spatial dimension, it uses something known as zigzag encoding. This is looking for spatial similarities among data. And finally, the data itself ends up being Huffman encoded. In some sense, this is using every compression trick in the book. Let's talk about audio on the DE1 board. There's an audio codec, which stands for encoder-decoder, that consists of an analog to digital converter for listening to audio and converting it to digital information, as well as a digital to analog converter that goes the other way. It has two 24-bit ADCs in it, two 24-bit DACs, a little headphone amplifier. It will sample as low as 8 kilohertz, go all the way up to 96 kilohertz, and operate on between 16 and 24-bit words. If you run this thing at 96 kilohertz at 24 bits, you're not going to hear the difference unless you have an incredibly good pair of headphones, and even then. The audio codec interfaces to the FPGA through essentially two serial interfaces. There's a slow one, this is the I2C bus, whose job it is to configure the codec, change the data format, change its volume levels, change how audio is being sent around the chip. Generally, you set this up once and you can leave it alone. The other interface is a so-called synchronous serial protocol. It consists of the data, a left-right clock that indicates to which channel the current bits are being sent, and a bit clock that indicates when a new bit has been sent to the codec. Here is an example of one of the serial protocols that the audio codec uses. There are 4 of these protocols, and you need to tell it which of these you're going to use, and this is what it will look for. This is one of the annoying things about this codec. If you tell it to listen to one thing and then generate another, it won't work, and it won't be clear why. The B clock signal is the bit clock, so this indicates when the next bit of data is being sent or is available from the audio codec. In this particular mode, data is sent most significant bit first, and then finally the least significant bit. The left-right clock indicates when the sample for the left channel starts and when the sample for the right channel starts, and you alternate between these two. Interfacing with this chip amounts in no small part to generating these waveforms appropriately. Finally, the DE1 has quite an idiosyncrasy when it comes to the audio codec. The designers wanted to be able to control the audio codec and the TV controller, both of which have I2C ports on them, from either the FPGA world or the HPS world, which has its own I2C bus. It's up to you. My thought is that it makes more sense to have the FPGA do the I2C configuration. Regardless, there is this switch control signal that goes from the HPS world, and you need to find that and set it appropriately, and it controls a switch that determines whether the I2C bus comes from the FPGA world or the HPS world. Do make sure you have this working, because without it you will not be able to configure the audio codec appropriately.